Today we're going to talk about continuous functions. Let's first recap some ideas that we talked about before. Say that A is a convergent sequence. That is, that we have terms x0, x1, all the way through xn, and so forth. Then, given a positive epsilon, there exists a delta such that in absolute value, x sub m minus x sub n is less than epsilon whenever both m and n are greater than delta. This then motivates what's called a Cauchy sequence. That is, given a sequence A, we'll say that it's Cauchy if, given a positive epsilon, there exists a delta such that in absolute value, xm minus xn is less than epsilon whenever m and n are greater than delta. We have a couple of properties. If A is a Cauchy sequence, then it is both a bounded sequence and a convergent sequence. This means that the following two statements are equivalent. First, that A is a convergent sequence. That means that there exists an element L such that, given a positive epsilon, we can find a delta such that in absolute value, xn minus L is less than epsilon whenever n is greater than delta. This is the same as saying that A is a Cauchy sequence. That is, given a positive epsilon, there exists a delta such that in absolute value, xm minus xn is less than epsilon whenever m and n are greater than delta. Here's the difference between the two. In order to show that a sequence is convergent, one must already know the limit L in advance. On the other hand, to prove that a sequence is Cauchy, you don't need to know what the limit is. But if you know that the sequence is Cauchy, then you're guaranteed that a limit must exist. Let's say that we have a bounded sequence. Then we know by the Bolzano-Weierstrass theorem that it must have a convergent sequence that we'll call B, and this must converge to some limit L. We've already seen that our sequence A need not be convergent itself. In fact, an example that we saw came from the logistic equation. However, if A does converge, then it must converge to the same limit that its subsequence converges to. Earlier in the course, we defined the real numbers in terms of Dedekind cuts. However, we can also define the real numbers by using Cauchy sequences. Here's the reason why. First, observe that any rational number, lowercase q, corresponds to the limit of a constant sequence. Again, we can define a sequence such that x sub n equals q, and in this case, it must be a Cauchy sequence and every term is the same, so it must indeed converge. More generally, let's say that we have a Dedekind cut. We can actually just choose S to be a non-empty set with an upper bound. Once we define L as its least upper bound, we can construct a Cauchy sequence from S as follows. For any non-negative integer n, let's denote epsilon sub n as 1/2 raised to the nth power. Since L is the least upper bound for S, this means that we can find an element x sub n in S that is epsilon n close to L. That means x sub n is in S, and x sub n plus epsilon sub n must be greater than or equal to L. We can actually show that this sequence, constructed in terms of the x sub n's, is a Cauchy sequence that has limit L. In other words, we can construct numbers in terms of limits of Dedekind cuts. Conversely, let's say that we have a Cauchy sequence. We know that it's bounded, so we can construct a Dedekind cut from this sequence as follows. Let's let S be the set of elements x in our field F, such that x is less than xn for some xn in A. Then S must be a Dedekind cut whose least upper bound is L, the limit of our Cauchy sequence. You can actually see this from the way that we actually proved that Cauchy sequences have limits. Putting all of this together, we now see that we can identify Cauchy sequences with Dedekind cuts. So if we identify the real numbers with Dedekind cuts, we can also identify them with Cauchy sequences. in order to produce a specific real number, we can either compute the least upper bound of our Dedekind cut S, or we can simply compute the limit of our Cauchy sequence A. We also see that the collection of Cauchy sequences forms a complete ordered field. In order to show this, you really must check that 14 axioms are true, but this gives us a completely different way of computing the real numbers. We can simply say that the collection of Cauchy sequences is a complete ordered field, and then define the real numbers as the limits of these Cauchy sequences. Today, however, we're going to talk about continuous functions. Let's start trying to get some intuition behind what a continuous function is. I'll show a few graphs, and I'd like to ask which are continuous functions. What about this graph here? Well, we can see intuitively it looks like the graph is all in one piece, and also everything seems to be connected. So we would say, yes, this is an example of a continuous function. Let's take a look at another one. For this graph here, it appears that this is disconnected into two parts. So we would say that this is a discontinuous function. What about this one? This here also looks like it's in one continuous piece. It looks like everything is connected smoothly. So yes, this is an example of a continuous function. And what about this last one? Although it looks like this is in one continuous piece, we see that unfortunately, this is not even a function at all. So there's no way this can be a continuous function. Let's give a more general definition. Let's say that F is a complete ordered field. Recall that given two numbers A and B such that A is less than B, the closed interval from A to B is the set of all elements X such that X is greater than or equal to A and X is less than or equal to B. Given such a closed interval, we say that our function is defined and unique for each X in the closed interval I. Given a point in our closed interval I, we'll say that our function is continuous at P if two things hold. One, the function must be defined at P, we'll call this L, which equals f of P. And two, given any positive epsilon, there exists a delta such that in absolute value, f of x minus L is less than epsilon whenever in absolute value, x minus P is less than delta. If this is not the case, we'll say that f is discontinuous at a point P. We'll say that a function on a closed interval I is continuous on I if it is continuous at P for every point P in the interval. Let's try to give some examples of graphs here to get some intuition behind what is the concept of a continuous function based on this epsilon delta definition. Here, say that we have a function which we know intuitively is continuous, but let's try to sketch how one would prove that this is continuous. We'll take a point, which we'll think of as P, and remember that we have P in the x-axis and f of P in the y-axis. Now, say that epsilon is given, and let's consider the following interval, which is in absolute value f of x minus f of P less than epsilon. What we'd like to know is whether we can choose an interval in terms of delta small enough so that the entire region f of x minus f of P is completely contained inside of the interval in terms of epsilon. Let's try this again with a different example. We'll pick a point here on our graph, and remember that this corresponds to a P in the x direction and an f of P in the y direction. Now let's choose an interval in terms of epsilon. What we'd like to do is say that we can choose delta small enough such that the region that we get once we map over to the y-axis is completely contained inside of the region in terms of epsilon. Finally, let's consider this graph here. You'll notice that this is not continuous everywhere because it's not even defined at certain points. This is what it means to say that the function here is split into two parts. Given a closed interval, let's say that f is a continuous function. We'd like to explain how this is related to sequences. Say that we have a convergent sequence A, and that its limit is a point P. Then, as long as f is continuous, we have a new sequence defined by f of xn, and the statement is that the limit of that sequence is f of p. Let's try to explain why. Say that epsilon is given. Then there exists a number capital N such that an absolute value f of xn minus f of p is less than epsilon whenever lowercase n is greater than capital N. In order to show this, since we know that f is continuous, we know that we can find a delta such that f of x minus f of p is less than epsilon whenever x minus p is less than delta. But A is a convergent sequence, so this means we can find our capital N such that xn minus p is less than delta whenever lowercase n is greater than capital N. But now putting both of these together, we have indeed found the capital N that we've desired. Namely, f of xn minus f of p is less than epsilon whenever our lowercase n is indeed greater than capital N, showing the limit that we desired. Let's try to explore this concept of continuity along with sequences in a bit more detail. But first, let's take a look at an example to get an idea of what should happen. We know intuitively that the function f of x equals x squared is continuous on the entire real line R. Let's consider a couple of sequences. First, we'll start with x0 equals 1, and then we'll recursively define the sequence by xn plus 1 is d times xn plus d divided by xn plus d. You'll recall that throughout the course, we've defined the sequence such that the limit of the sequence is just the square root of d. So what we expect to happen is that if we take the limit of xn, then this should be the square root of d squared, namely d itself. Let's try to see what's happening here numerically. You'll see on your screen a few different values where we have d is equal to 2, d is equal to 3, and d is equal to 5. On the left, where d is equal to 2, you see that we've started with x0 equals 1, and we've iterated to look at the first 10 terms of x sub n. We've also evaluated f, namely x squared, at x sub n to see how the number should increase. It should make sense that the x sub n's increase to the square root of 2, whereas the f of x n's should increase to the square of the square root of 2, namely just 2 itself. We know that these are all monotone increasing sequences because of the way that we've defined our x sub n's. We saw in the past that the x sub n's should be an increasing sequence, and because of how the function f of x equals x squared behaves, we see that f of x sub n should also be a monotone increasing sequence. Let's try this with a slightly different set of sequences. Let's consider the following, where x sub 0 equals d, and now x sub n plus 1 is 1/2 xn plus d over xn. Again, the limit of the xn should be the square root of the d, and the limit of the f of xn should just be d itself. But remember how we chose the sequence xn to begin with. We know from previous lessons that this sequence should be a monotone decreasing sequence. And again, based on the behavior of the function f of x equals x squared, we expect that the f of xn's should also be monotone decreasing sequences. Indeed, we can see this from the behavior that we have here on the screen. If xn starts at d, it will slowly decrease to the square root of d. And we expect similarly that f of xn should start at d squared and decrease down to d. Let's state a general result based on the previous proposition about sequences. Let's say that we have a continuous function f. We know that if we have a bounded set S in our closed interval, then both the supremum and the infimums of S should exist. Remember that the supremum is the least upper bound and the infimum is the greatest lower bound. Indeed, our closed interval I is actually a bounded interval, so it makes sense that both the supremum and infimum of f should exist. Let's assume for the moment that our function f is increasing. That is, f of x is less than or equal to f of y whenever x is less than y. Then the supremum of s, which is a real number, will map to the supremum of f of s, which is also a real number. In this case, f of s is a sequence that we'll take a look at in just a moment. Let's assume that f is decreasing. That is, f of x is greater than or equal to f of y whenever x is less than y. Then the supremum of s is a real number, and we can consider f of the supremum of s, which is another real number. The infimum of f of s is also a real number, and the statement is that they will be equal. Let's try to explain why this is all true. Let's let p be the supremum of s. Remember, s is some subset of the closed interval from a to b. This is a bounded region, therefore the supremum of s, that is, the least upper bound, should exist. We'll find a convergent sequence contained within s that has p as its limit point. To this end, let's take a look at f of a, which is where we'll apply f to each of the elements in our convergent sequence a. We know that this is contained in f of s, which is just the collection of f of x, where x is an element of our set S. Since f is increasing, then this sequence f of a must be a monotone increasing sequence, which is bounded above by the real number f of p. The Bolzano-Weierstrass theorem states that the supremum of this set f of s must be equal to the limit of our sequence f of a, which is just f of p. But as we said above, we defined p as the supremum of our set S. There's a similar argument if f is decreasing, where now we see that f of a is a monotone decreasing sequence. Thanks very much for watching.